Hello and welcome to another Developer Essentials. So this time around, we are going to be taking a look at the area of profiling. So the idea behind profiling is it's about working out how our code is actually performing. So how is it running, and this is not just in terms of, okay, is it running fast, but looking at, okay, are there parts that are running slow? If they are, where and why are they running slow? Is it that we're running something way more times than we need to? Is it that we've got something that takes a very large amount of time to run, but we're only running it a few times? Are we running into issues because of memory? So profiling is looking at not just CPU usage, but also memory usage. And we can also be looking at things from the GPU side. All of these are areas that we potentially can run into problems with. So we want to actually have a look at how can we get a bit of a sense of what's actually happening there. So one of the things that will often cause us in the early days to start needing to profile something is we'll see that it's running slow. So we're going to take a look, and if you haven't seen this before, when you're in the game view, one of the things that you can bring up is you can click on stats here. And this is a really useful thing to have up. And so I won't have this running from the very beginning of a project, but once I've got enough sort of a representative level of the complexity, I will actually turn this on, in particular for GPU side things. So frames per second is a useful thing to be looking at. And in particular, what I'm generally looking at is if that's getting to low values and then starting to look at things like, okay, how many batches are happening there? So essentially how much stuff is being sent to the GPU in terms of work there to be performed. So I'll have a bit of a look at things that we can be doing with that. First, we're going to take a look at profiling from more the CPU and memory side. So to do this, I am actually going to make some really terrible code. It's one of the easiest ways to do this is to set up some really terrible code. Conveniently, I have a long library of previous things that I've written that have ended up being really slow and that I've learned how to make them better to refer back to. So this is going to be profile demo 1. So this is going to just do a couple of things that are going to be horrendously slow. And some of the things that can be really slow actually might be things that we don't expect to be. It's not always an obvious thing. And with profiling, an important thing to consider with this comes into optimization, and that is we don't want to optimize things too early. Highly optimized code is often really, really hard to read. So profiling and optimization is an important process, but it's not something where it's a case of, cool, I'm 1 hour into a project. First thing I'm going to be doing is profiling and optimizing it. You want to get to the point where you've got a representative level of complexity. Obviously, if you've implemented something and you know that it might be performance heavy, then you would implement it and profile it afterwards. But it's not something where you need to obsess over doing the profiling once you've just done a few small things in the project. So what I'm going to do is things to spawn. I'm going to say I want it to spawn 1,000. I'll have a spawn delay. So what I want is just something that after a few seconds, it's then going to run this process that's going to be horrendously slow, intentionally. So what we're going to do is f spawn delay is greater than 0. Then we just update the time. And then just as a final thing, if it's still above 0, then we can just early out. Now what we're going to do is spawn a whole bunch of things. Count 0. So I just want to do a whole heap of spawning because this is something that memory allocation there's going to be a bunch of things associated with that that are going to make it slow, which is what I want. Anytime we're working with stuff with memory, especially if we're doing a lot of small allocations, that actually can be horrendous for performance. So if you've got to allocate a lot of stuff, then that's something where if you can, you want to try and allocate that a bit over time, or look at ways of being able to more efficiently spawn stuff only when you're needing. Which ties into another area called object pooling, which we will also be looking at another video that will be out shortly. So I want to spawn some things. So firstly, let's pick a spawn offset. So random range, and I'm going to have a spawn distance. So all I'm going to do is spawn a lot of stuff just in a random locations around my current location. So minus spawn distance to spawn distance, and we'll just do that. So it's essentially we're spawning ones in a sphere around us like that. So then what I can do is I can instantiate a primitive. So I think it's create primitive. Direct one under game object, create primitive. So primitive type, well, let's spawn something that's going to be a bit more complex, a sphere, more geometry, a bit more overhead there. So we'll spawn a sphere and new object, transform position, plus offset. So this is probably going to be quite slow. So after 5 seconds, I would expect to see potentially a massive jump up in the number of batches and also a massive impact there in terms of potentially the frame rate, things like that. So let's just run it and let's see if it's obvious first just in the stats window. Then we'll show you the profiler window where we can see a more detailed one. So we can see immediately, and we did, because we are spawning 1,000 things, this number of batches is horrific. Genuinely a horrific number of batches. And so that, we saw a noticeable spike there. So that's good. So let's see how we can go about profiling that. So under window, and then under analysis, we have profiler. And there's 2 different versions of profiler here. There is profiler and it's profiler standalone process. So profiler is one that's going to be running in the same context as the editor, which means that it's going to have a little bit more of an impact there in terms of editor overhead and things like that. The standalone one is likely to give you more accurate profiling results. So we'll take a look first just at the integrated profiler, and what I'm going to do is I'm not going to do a recording, but I'm just going to run this, and we should see it'll start just automatically recording data. And we can see information's coming through, which is good. And very shortly we hit our massive spike, which conveniently is very, very visible in the profiler. And this is what we want. So let's start to look and see the different bits of information we get from the profiler. So we have our general sort of overview one here, and this is giving us information like our CPU usage, and we can see time that's going to things like rendering. We can see time that's going to different areas. We also have these horizontal markers for our frame rate. So as this goes up, so higher values here means stuff is running slower, it's running worse. And so we can scrub through our frames, and generally we're looking for things like this. We're looking for peaks. We can then take a look and see in other things. So We also have, for rendering, which you already know, we've got 26.5 million triangles and 34,000 batches, 34,000 draw calls, horrendously expensive. We will have a look at how we can simplify that as well. We can see memory usage, which is really handy. We can see where that memory usage is going in terms of textures, meshes, materials, things like that. Really great to get a sense of the memory pressure that our project might be under. In this case, not too much in the way of memory pressure, which is fair because what we're allocating there is not going to be particularly large in memory, but it's a useful thing to be checking. Audio, it's an area that people can easily forget that audio takes up memory, and the more complex your audio is, the more intricate, the more sounds you've got playing at any point in time, the more memory it's going to take up. So we do need to be cautious with that. We can see in terms of with video, so that's for if you had an embedded video playing. Can see impact for things like a physics. So again, a physics-heavy game is going to have a fairly complex setup there. In this case, we can see 31K for static colliders. So it's getting quite expensive. And so we've got lots of different areas where we can see stuff in terms of different features like the global illumination, because I've got real-time lighting on. So lots of data that we get here to get a sense of how are different things performing. Are we running into CPU issues? Are we running into GPU? This gives us sort of a good indication for that. If I go back to CPU, down here in this hierarchy is a really important area. So we can see where the time is going. So we can see 49% of the time is going to editor loop, which we'd expect. That's that overhead there with the editor. And 49% is going to the player loop. So 28 milliseconds is going to the player loop. And we can expand this so we can see where that's actually going. 44% of that is just the camera render. And we can see the different components that are affecting that. So it gives us a good way of breaking down where the different things are. So this allows us to get a sense of where the slowness might be occurring. We can see the particular things. So this is, in this case, behavior update. So we can see our particular functions, and we can get a lot of info there. We can see add component is taking up a chunk of that time. We've got different little bits of info there that we can see. So it gives us a way of knowing how much time is being taken up with something. And importantly, the things we're generally looking at with this is the number of times something has been called. Because when we need to optimize something, we either need to make it that actual action take less time, or we need to do it less often. So if we have something like this, we've got a large number of calls, that's something where, well, if we could slow that down, if we could spread that over multiple frames, then we can level out the performance and remove the spikes. And that's often a big thing that we're trying to do there is remove spikes. So spikes will be far more noticeable. So if your game's frame rate is spiking, that will be much more noticeable than if it's at a consistent lower level. So if something's running a lot like that, then we can actually eliminate that and make it so that we're running at less times. The other thing is if something is running really, fast and a huge number of times, then our only option is going to be to cut down the number of times. Because we have some things that the actual operation is really fast. We're just doing it so many times that it's taking a lot of time. So delaying things, being able to run things, or just spread, distributed over frames is a really valuable thing there. And the profiler is how we get a sense of where that's happening. Now, with this, we can get more information, and we also have different ways we can view this. So we can view sort of a timeline view here, and we can see what stuff is happening on different threads. I generally find this hierarchy view is the one that is easiest for me being able to understand, because the self percentage is how much percentage of the time was just within that function. So not other things that function called, but just the general overhead for that function itself. And the total on there is what percentage of that frame this function took up. So as I said, play a loop, I can see that that's taking up nearly half of our time and about 28 milliseconds. So I generally, when I'm trying to work out which things to optimize, I'm usually going and looking through this time in milliseconds. And then if I see a really high self value here, either for the self milliseconds or a really high self percentage, that tells me that the overhead is within that function itself and not something that that function is calling. So for example, our behavior update here, we can see that with a time of 1.81 milliseconds, 0.38 of that is just general other stuff that's happening within the function. The rest of that time, the bulk of it, is taken up by add component. That's how we can interpret these. Now, we can get more detail than this if we want. So we have this option here called deep profile, which I'm not going to turn that on. Deep profile is something that we do need to be very cautious with using because its overhead is significant. Because sometimes we can't get particularly detailed call stacks here, but a deep profile will give us that at the cost of it being much more overhead and much more expensive. So it will tell you that an area is slow, but it's also itself going to be impacting on performance a lot. Now we do have an alternative where we can actually mark up sections of our code. So what I can do is I can set up things here where if I bring in using Unity Engine profiling, I can set up some markers, some custom markers for stuff. So static read only is generally what we'll use for these. So these are profiler markers. And what we can do with these is we can actually then give sections of code a particular name. So spawn loop. It's a new profiler marker, and we can call that spawn loop. So to be able to access these profile markers, it's unity.profiling. There is a Unity engine.profiling, but these markers are actually in unity.profiling. So do be cautious of that. And then the way we can use these is, for example, we can do using spawn loop auto, and then we just wrap our code in it. So it's a way of just marking sections like this. And then we're going to run this again, and we're going to see what we see in terms of data now. Because the idea behind these profile markers is to block out different sections so that we can actually get a sense of narrowing down that particular area for its time impact. That should be enough. So if we go over to our profile, select our CPU one then with that set up, we should be able to get a little bit more info in terms of when we go over to our ones here. So we have the name here will actually appear. So it means that we can give proper names to our areas there. And it also means within a particular function, if we had multiple sections in a function that we want to profile very cleanly, distinctly, we can do that. We can set up different sections there for it. So for example, I might have then a cleanup section that ran afterwards. I could do another using with a different marker, and that will have them split out as separate areas. So it means that we're just able to capture the time that's taken for that particular spot, which is great. So key things with the CPU profiling is that deep profile generally really usually try and avoid that unless it's something where we absolutely have to, because it does have a huge impact. So the main thing we're wanting to do is we get the slowness to happen. We select the particular frame that we want to look at, and then we take a look in our hierarchy. And what we are focusing on is we are looking for ones that are taking up a large percentage of the time, a large amount of time there. And we're looking to see how many times are those running and how long is it actually taking. That gives us a sense of whether this is a case of, well, we need to run this less, or we need to try and make the action that it's doing faster. If it's only doing it a couple of times, then we need to make it faster. If it's doing it lots of times, then we might be able to make it faster, or we might need to make it that it runs it less often. So we can navigate through that, we can find our particular sections, and we can use these profiler markers to section off areas of code so that we can get a sense of, how those are particularly performing. Similarly with memory, we can actually get more detail with memory, and it is possible to actually profile the memory and get a sense of where we're using that. It's less commonly needed for most of the stuff you'll be doing. CPU side and GPU side are the main ones you're likely to run into at this stage. So we've seen CPU, seen where we can check for memory, and we've seen certainly GPU-wise, this is getting to horrendous numbers of batches. But what if we want to understand why is that happening? So that is where our frame debugger comes in handy. So it's also under analysis. We have this frame debugger. So we'll turn that on and we're going to run. And then what we're going to do is we're going to let it get to a stage where we've got the horrendous performance. That looks suitably horrendous. So we'll turn on the frame debugger and then we can stop this. So now we can take a look and inspect what's actually happening. So if I'll pause it. So you do need to be cautious with when it's running there. So I'll wait till it's running, then I will pause it and capture that and look at that. Cool. So that looks pretty suitably slow and horrible. Excellent. So we can see what's actually happening here. And I'm going to bring this up so it's full screen so we're not continuing to render stuff. So the frame debugger, what is really powerful about it, because we saw there's huge numbers of batches, and we can see when we take a look at this, there's horrendous numbers of batches happening here. What's powerful with this is it will tell us why it has not actually batched something. So, and we see how many of these things are there, so how many times it's doing each particular thing. So we can see, okay, lots of stuff for shadows. So we can click on a particular sphere, and so we can see which thing it's actually corresponding to, which incredibly powerful and helpful with that. And then we can also see our particular individual ones that are actually there and running. So we can get a bit of a sense there of what's actually on display and where these particular ones are, in the actual game world. So that is super handy, and when we have the actual view here, we are able to see a bit more information. So with the view there, we can then go and actually select particular things. And what you can see, and this is where it's really powerful, you can see why it didn't batch. Because we've got huge numbers of objects here, and it's not batching them. And the reason why it's not batching them, it will tell us. So this is what's great about it. It tells you, so firstly you can get a preview, you can see what you're actually rendering, but this information here can't be batched because it doesn't have GPU instancing enabled. So that's something where if I go and set up a material, and what I will do is I will actually, material for the sphere, I'm going to turn on GPU instancing, and I'm also going to create a prefab for that sphere. that's going to have that particular material on it. And then I'll instantiate that prefab. The fact that it's a prefab I'm instantiating doesn't make any difference in terms of its performance. The performance difference comes from the fact that I have that GPU instancing enabled. So I've got the sphere material. I'm going to make this a different color just so we can easily tell. And then I will set up the object prefab to spawn. Instantiate. So not much different to before. If I had GPU instancing off, I wouldn't see any improvement there. The improvement, as I said, is going to come from this fact that the GPU instancing is enabled. So let's run it now and let's see what we have in terms of batches. So it'll kick into the point where it's going to start spawning before too long. So it's now spawning. We can see a couple of key things. Our frame rate is held more steady, and the number of batches is way lower, orders of magnitude lower than what we actually had before. And still getting there and spawning all of the particular ones, but significant improvement over where it was before. And if I pause this and again bring up my frame debugger and enable that. So firstly, we can see huge difference in the number of draw calls, significantly fewer draw calls. And in particular, this forward loop job, you can see what it's doing, it's draw mesh instanced. So significantly fewer ones. And we can see now, it still gives us information on why there are other batches, and that's because it's reached the maximum instance count. So what batching allows it to do is if you're drawing the same thing multiple times with the same material, then it can doesn't need to send that same thing 500 different times to the GPU. It can send it fewer times, and then the GPU can place it at multiple locations. So we're sending less data, and that allows it to perform significantly better. So the frame debugger is really powerful for getting an understanding of why you're seeing a large number of batches. And conveniently, it even tells you here, I'm saving 80,035 batches, which is a huge number. So GPU profiling, really handy if you're seeing frame rate issues. One of the big things to watch for there is this number of batches. It's very easy to forget to turn on GPU instancing. It's on a material, it's a really common thing to forget to turn on. The other one that you may not have turned on is if we go to, it's usually under other settings, dynamic batching is another one that in this case probably won't see much of a difference in performance, but it can show us a big improvement in performance. This allows it to dynamically build up batches again at runtime. And so again, we're going to see it's a fairly small number of batches, even with just so many things being rendered there. So the dynamic batching for a scenario like this is probably not going to make a huge difference. We'll more see that in the case of ones where it's not, thousands of spheres that we're actually trying to be drawing. But the important thing is using those tools to get a sense of where the performance issues are. So key things that I recommend and key ways I'd say about how you approach profiling. So firstly, don't feel that profiling the code and obsessing over the performance is something you need to be doing from the first moment you've written any lines of code. It's not, and it shouldn't be. Optimizing, premature optimization is a problem with projects, and it's very easy to spend a lot of time doing that for not necessarily a lot of gain, and highly optimized code is much, much harder to often work with and maintain and debug. So, points of where you decide to optimize. If you've implemented a major thing, then you know that it may have performance implications. Then that is a good point to, as part of that development, profile it and test the performance. So if you're implementing procedural generation system, a pathfinding system, anything where it's a larger scale system you're implementing, do some profiling of it. Check its CPU performance, check its memory performance, its GPU performance, if it's a rendering side one. So when you've implemented a particular thing, outside of that, once you have a representative complexity to your scene and project, so if it's in terms of representative visual complexity, that's where you would then start to look at your CPU, GPU, memory. If it's something where you've just focused on purely the GPU side and getting some test cases up for that, might be some particular visual effects. That is a good point to then do that sort of profiling, check the frame debugger, things like of that. For CPU, what we're particularly looking for is avoiding spikes. Spikes are super noticeable. A lower consistent frame rate will be less noticeable than a high frame rate that at times spikes down. So we want to avoid that. From the GPU side, if we have our stats window up, which usually when I'm developing projects, I have this up the majority of the time because I want to keep an eye on things like the number of batches and the frame rate. Those will give you a good sense of am I running into performance issues. When you do get stuff there and there are performance issues, if it's CPU ones, look and see how long stuff's taking and how much it's running. If it's not running many times, but it's slow, see if you can run it faster, maybe divide it up into different chunks. If it's running lots and lots of times, then see if you can make it run less times, even if that's spread over multiple frames. For the GPU side, if you're seeing lots of batches, use the frame debugger and get a sense of why are you seeing lots of batches. Maybe you need to set up instancing on the materials. Maybe you need to enable dynamic batching. You've also got occlusion volumes that you can build. All of those things will help with the performance there for it. But the key thing is be methodical with it. Get a sense of what the actual problem is, get a sense of the size and the scale of it, and then plan out and make your changes. Don't go for a sort of haphazard approach with it. Don't optimize stuff on the basis of, yeah, this is going to be slow without actually profiling it. You can be surprised by what things are and are not slow. So make sure that you're doing that testing and being methodical about it so that you're spending your time where it needs to be and that you're fixing the right particular problems. So dive in and experiment with this stuff. If you've already got other projects, profile them. See how they perform GPU-wise. See how they perform CPU-wise. Test those different ones. If you're wanting to grab any of the projects there that I've got up on the GitHub, grab those and profile those and see how those are actually running. See what you can do in terms of ways of making it faster. But the key thing is dive in and experiment with it. And if you've been finding videos like this helpful, please do chuck in a like and subscribe. It really does help out. It's really appreciated. If you've got any questions, do chuck in a comment below. If you're looking for other ways to support the channel, I do have a Patreon, and the links to that are also in the description below.